Last three classes we covered the principles of thermodynamics, microscopic balances and macroscopic balances. Today we will apply what we have learned for the last three classes to cargo containment system and the reliquefaction system of LNG carrier. Usually the thermodynamic, in our field, the thermodynamics is critical to the design of offshore plant, gas or oil processing plants. But I think their system is too complicated for you to understand. So I prepared this application example because it is relatively simple compared with the offshore plants. I don't know why, but as you know, there is some lines here. Usually, LNG carrier has 4 to 5 cargo tanks, and the stored LNG temperature is around minus 160, and the pressure is atmospheric. All the bulk gas carriers is under the pressure of atmospheric pressure. Commercially, there is no pressurized bulk gas carriers. CO2 is an exception because under the atmospheric pressure, CO2 should be in solid form. But for LNG, LPG, ethylene, and all the ordinary cargoes, the carriers are the cargo containment system for the carriers are under the atmospheric pressure. The blue line is called LNG header, and if you want to offload, the same words. If we discharge, unload LNG from the tank to the carrier, we use a submerged pump. The pump pumps up LNG, and it goes through the LNG header and to the terminal. Because the temperature difference between the cargo tank and the atmosphere and the seawater is significantly large. It's about 190 Celsius. We cannot avoid the heat ingress from the outside, and the heat ingress causes some boiling. So this boiled gas is called void of gas, VOG, simply. And this VOG should be, historically, this VOG has been used for fuel. Fuel for boiler, and the boiler generates steam. The steam drives the steam turbine. The steam turbine drives the propeller. But nowadays, the new concept was introduced, that is to liquefy this VOG using the reliquefaction system. And the reliquefaction system liquefies VOG and returns the condensed, reliquefied LNG to the LNG cargo tanks. This is the overall cargo operation concept for LNG carrier. Any questions? one thing you should know is that LNG is in the boiling state. Okay, actually it is boiling very slowly. You remember the normal boiling point? Normal boiling point in the phase diagram. The normal boiling point is the boiling temperature under atmospheric pressure. Okay? Boiling point at 1 bar. Actually, the cow LNG is at the boiling point at 1 bar. This is the typical concentration, the composition of LNG. Methane, CH4, takes the lion's share, about 90% of the LNG. And the second largest component is ethane, C2, and propane, butane. Propane, butane are the LPG components. Usually LNG has a trace amount of propane, butane, and there are a lot of other heavier components, but their proportion is very small, so you can neglect their presence. Another component is nitrogen. Most LNG contains a small amount of LNG, but it caused some problem. In this, let's compare the normal boiling point of the components. Methane's normal boiling point is minus 164. So you can say that the cargo temperature of the LNG tank is 164 because the methane is the majority. Nitrogen's normal boiling point is minus 169. It's nearly 200, minus 200. That is, if there is no methane, this nitrogen should be in gaseous state. But we have a bulk of methane, and nitrogen is dissolved in the LNG. Can you understand? We have water here, and the majority of this water is water, okay? But small amount of oxygen or nitrogen can dissolve into the water. So nitrogen is kind of is the oxygen to the water. No? We have a big beaker. We have water. Okay? Maybe 99% of this material should be water. But small amount of air, I mean the oxygen or nitrogen, can dissolve into this water. You agree? The same reasoning can be applicable to the LNG. We have a large amount of LNG here. The majority is methane, and small amount of nitrogen can dissolve into the LNG. Actually, the nitrogen concentration is 0.3%. Then assume that in the water oxygen solution, if we warm up this mixture, what happens? If the temperature is less than 100 Celsius, we cannot observe rigorous active boiling, but we know that oxygen will vaporize first. Because the solubility of oxygen decreases with the temperature. So if we increase the temperature, if we check the vapor composition of the evaporating vapor, we can observe a significant amount of oxygen. This kind of reasoning is also true for LNG. That in LNG, the majority is methane, and nitrogen is kind of a trace component. Very small amount of nitrogen only exists. But if we check the VOC mole fraction, nitrogen nearly takes 10%. Why? Because normal pointing of nitrogen is far lower than methane. The difference in normal point is around 30 Celsius. So if we check the vapor composition from this cargo tank, if we check the composition of VOC, we can observe a large amount of nitrogen compared to that of LNG. Any question? Silence means yes. I think there we miss some part of the figure, but you can see the material. There are three kinds of cargo tank types for LNG carrier. One is actually two kinds. One is the box type. The other is spherical type. And the box type is usually called membrane type. Membrane means it's a small thin layer compared to the hull structure. But you will see the thickness is not that thin if we include the insulation layer. Let's check later. Anyway, we have a box type, cargo containment system. One is Mark III, and the other is NO96. Originally, Mark III is a patent of TGG. NO96 is owned by GT, but unfortunately, these two companies were merged into GTT. And they we need the Korean shipbuilders need their license to build membrane type LNG carrier. That the license fee is a little high, so there have been many attempts to develop our own tank types. Another type is spherical, originally developed by Moss, so it is usually called the Moss spherical type. Nowadays, membrane types are dominant over the spherical type. This figure shows an LNG carrier in a dock of Hyundai Heavy Industries. This is the membrane type LNG carrier. You can see the bulb, hemisphere, hemisphere means semi-sphere. Hemisphere on the deck, but actually it's a sphere. The lower half of the sphere is within the hull structure. This is the membrane carrier. So if you consider the three-dimensional layout, a spherical type has a significant disadvantage. It needs some empty space because the cargo tankers are spherical. We have a sphere here, another sphere here. So these spaces are empty. To avoid the heat ingress from environment, the usual way is to apply insulation layer. For the spherical type, these are insulation layer, the yellow and light green, and these blue ones are the insulation layer. For membrane type, the structure is a little complicated. The insulation is multi-layer, as you can see in your homework. Did you check your homework? Not yet? You can see the table for the membrane, the multi-layer structure of the membrane in your homework. Actually, this structure for Mark III membrane. It has 7 layers: primary barrier, top plywood, primary insulation, triple X, secondary insulation, back plywood, mastic. Plywood, insulation, check the material. Primary membrane is made of SOS, stainless steel. Top plywood, RPUF means polyurethane foam. And aluminum foil, urethane foam, plywood, epoxy. You may heard about this kind of material: plywood, epoxy, polyurethane foam. These are commonly used for insulation. Check the thickness. That SOS, stainless steel, thickness 1 millimeter. Okay, and secondary insulation. Triple X is also 1 millimeter. These two are playing the role of containment, and their role is to prevent leak from inside to outside. So the thickness is a little thin, 1 millimeter. Okay, we have two 1 millimeter layer to contain the LNG inside it, and others role is insulation against heat ingress. I will give you a detailed description. It's not a detail. I'm the overall philosophy of the cargo containment system. One important thing is pressure protection. Cargo tankers are designed to carry the cargo near the atmospheric pressure, but we have a BOG, and the BOG will increase the internal pressure. So the BOG should be removed from the cargo tank. Otherwise, the tank will generate leak. So the BOG should be removed against the overpressure. There are several protection layers. First is if the pressure is too low, that less than 1 bar, we call that kind of state vacuum. If the cargo tank is under vacuum, we need to insert some gas. So maybe easiest way is to insert the air, but if you insert the air, the air ambient air within the cargo tank would be flammable. It can explode. So usual way is to vaporize LNG and insert the vaporized LNG into the cargo tank. So vacuum pressure protection against vacuum is very simple. Vaporization of LNG and insert the vaporized LNG into the cargo tank. High pressure protection has two layers. One is if the cargo the pressure is high, BOG should be removed the tanks, and the BOG are supposed to be liquefied in the reliquefaction system and returned to cargo tank. But if the reliquefaction system get failed, the BOG cannot be reliquefied, so the BOG will build up in the cargo tanks and the pressure will increase. In that case, we have no choice to just vent out the BOG. So for the venting, we have safety valves. The safety valves on the cargo tanks are opened and the BOG is vented. So venting BOG can cause fire or explosion. So it should be treated safely. So one choice is to burn the COG, and the unit is called the unit to burn the BOG is called the gas combustion unit. Again, some parts are missing in this slide, but the concept of reliquefaction system is very simple. We use nitrogen, and if we apply the compression, cooling, expansion concept to the nitrogen cycle, we can get cold nitrogen around minus 70. Then the cold nitrogen is supposed to cool down or liquefy the BOG. That is the concept of BOG reliquefaction plant. But the concept is very simple, but in reality, the process becomes complicated for safety, for efficiency. So let me show actual process. This process is developed by a consortium. The consortium was led by Shinyoung Heavy Industries and major shipbuilders, including Hyundai Heavy Industries, DSME, and Samsung Heavy Industries, participated in this project. Personally, I participated in this project and designed this process. Let me explain the process shortly. BOG is the temperature of this BOG is around -100, and this BOG is warmed up and compressed around to 8 bar, and after 8 bar it is cooled with seawater, and this is returned to the cold box. This cold box is cooled by nitrogen cycle. So we have some BOG exchanger. The role of BOG exchanger here is very important. That if cold BOG is inserted to the compressor, we need a special compressor to handle the low temperature gas. So the policy is that is taken in this process design is to exchange heat between this stream and this stream. This stream is cold, this stream is a little high. So if this the temperature of this stream is -100 and it's about 40. This stream temperature -100. This would be 40. Then if we take the approach temperature as 10 Celsius, the only temperature would be -90. This temperature would be 30 because the mass flow rate of the two streams are the same. So by employing this concept, we can use the normal compressor, the ambient temperature compressor, and it is cooled and liquefied, and finally it is sent back to the cargo tanks. Let's check the nitrogen cycle. We have a nitrogen cycle here, and that nitrogen is compressed from about the 16 bar to 60 bar. And after it is cooled a little, and it is expanded through this turbine, then you can get nitrogen at -170. Then nitrogen is capable of liquefying the BOG. And through some heat exchange, the returned nitrogen temperature around room temperature, 10 to 30 Celsius. Any question? Yes? There are some thermodynamic questions. Of course, there are a lot of challenges to the system design. But in this class, we concentrate on the thermodynamic questions. Energy transfer, heat transfer, and system design. So for the convenience, let's divide the system into two. One is cargo containment system, the other is a BOG reliquefaction system. And cargo containment system includes cargo tanks, pumps, insulation headers. BOG reliquefaction system contains the BOG cycles and anticycles. So I selected some questions. The first one for the cargo containment system is amount of heat ingress, how much the heat ingress is. The second, the amount of BOG generation and its composition. Third is pressure increase, EOG, BOG generation. And the selected questions for BOG reliquefaction system is first, minimum and actual energy required for reliquefaction, and the thermodynamic model for the machinery component. But I think the last two questions are a little difficult for you, so I will concentrate on the first three questions. To solve this kind of, to answer this kind of questions, we need some background, conservation of energy, mass, momentum, and phase equilibrium. So for the last three classes, we touched the surface of this. Actually, I tried to remind you of what you learned during your undergraduate days. So we followed this path already. We reviewed the law of thermodynamics, first, second, third law of thermodynamics, and we checked the non-disputed and steady balances. And we our reasoning based on ideal gas. Then on day 2, we reviewed the conservation of energy, mass, and momentum. And first, we consider microscopic balance, and we attempted to describe the conservation based on differential equation. And the second half of the day, we studied the macroscopic balance for systems. Macroscopic balance is inevitable for system analysis, and most of you, we involved in system design, and the ships and offshore plants are basically system, not a small world. They are kind of big world, requiring hundreds or thousands of small items or subsystems. So you should be familiar with system level thinking. So we checked how to derive the macroscopic balance. Basically, the concept of balance are the same, and the concept of macroscopic balance is the same for the microscopic balance. And 2 days ago, we checked the phase equilibrium. First, we considered the pure component system. Then, we moved to multi-component system. And we checked the phase diagram and normal boiling point and the boiling range for mixtures like the dew point, boiling point. I'm sure you can remember everything. Consider the first question, the amount of heat ingress. Our mission is to estimate the heat ingress. How much heat should ingress into the cargo tank? It's the first question you should answer. So now you have a big cargo tank, and first thing you should do is, what kind of governing equation should I take? So this problem is about energy. Heat is energy. So we consider heat, conservation of heat. There are several approaches, but in this case, we can apply microscopic balance. So in this example, the governing equation is this: the microscopic balance for energy when there is no moving flow. We have only solid structure, and for that situation, the governing equation, actually the original form of governing equation is very complicated. But when we deal with solid structure, the solution becomes simplifies into this form. So this is the governing equation. Actually, we don't need the material derivative because the flow rate is the velocity is 0. Material derivative is you remember this operator? Yep. But within the solid structure, U is 0. So material derivative equal to this operator, a partial derivative with respect to time. So our so we if we have the structural analysis tool, and you can solve this equation, then you can get the temperature distribution. We need boundary condition. So boundary condition would be that if we have a structure here, LNG here, so the boundary condition for the LNG contacting surface would be minus 164, and the boundary condition for the under outer surface is, what is the proper boundary condition for the outer surface? There would be air or seawater. So you can impose the boundary condition of 30 or 10, depending on the boundary condition. Actually, the detailed structure of the ship is like this. We have insulation layer, and we have inner hull here with some void space here, and this is the outer hull, and outer hull is contacted with the air or seawater. So the temperature on the outer hull should be like 30 or 10. So since we have a void structure here, usually the boundary condition is usually put like 0 Celsius. So what is important is that you should know the detailed structure of the cargo containment system and the neighboring structure. The boundary condition itself is not important. What I mean is, that you should know the inner structure of the ship. So if you have a structural analysis code, you can generate a mesh and impose some boundary condition, then you can have temperature distribution. If you have temperature distribution, the heat flux is given by this equation, minus thermodynamic K minus K times temperature gradient. If you integrate this heat flux over the whole area, you can get the total heat ingress. In real world, in your real job, what you can do is that if you know the structure, if you know the basic reasoning, and if you know what you should order the program to do, then the program will take care of the rest. You should know this inner structure of the ship, inner structure of the insulation layer, and you know the proper boundary condition. Then the program, the structural analysis program will take care of the rest. They will solve this equation, and the program will calculate the heat flux. The program will integrate the heat flux over the surface. Any question? This example is to estimate heat ingress into one tank during the cooling down from 45 Celsius. You built a new ship in a summer day, so the temperature is a little high, so the ship owner and in order to commission the ship, the cargo tank should be cooled down. So usual way is we spray LNG from the other tank to the tank, and the sprayed LNG will, the mist LNG will vaporize, cooling the tank, cooling the insulation and to some and the inner hull to some degree. So the ship owner impose a relatively extreme hot condition. So the temperature, the initial temperature of the cargo tank was given at 45 Celsius. Okay. Even in this case, you can apply the same carbon equation, and with the boundary condition, the initial condition that all the insulation layer should be at 45 Celsius. Then we solve this equation. The mesh structure and the initial condition 45 Celsius, and we spray, then the air within the cargo tank will decrease, and the decreased air temperature will cool down this cargo tank. Usually it takes tens of hours. Anyway, this is the actual calculation. I mean that this hour it took around 30 hours to reach the steady state, and 1 rack, 2 rack means the nozzles. I mean that within the cargo tanks there are 2 racks of nozzles, 1 rack and another rack, because the cargo tank is a little huge space. So the temperature, I mean the initial response can be different, but from the viewpoint of the steady state temperature, 1 rack is also sufficient. So following if you solve the carbonic equation, you can get the heat flux into the insulation layer. This graph shows the actual calculation result. Let's get back on track. The second question is the amount of VOC generated and its composition. The solution strategy is very simple. We solve the multi-component phase equilibrium problem. And we have LNG here. And as I told you, LNG is in the boiling state. Okay? Actually, LNG is boiling in the stored condition in the cargo. So then how to solve the multi-component phase equilibrium? I show you some thermodynamic relationships about the partial pressure and fugacity. But in real world, that kind of program is highly nonlinear and hard to solve. But we have program. The process simulators. In the previous example, we used the commercial codes for structural analysis. In this case, we can use commercial codes, a commercial program for process simulation. So you input the composition of LNG, and if you set the temperature, then you can get the pressure and the vapor fraction, vapor composition. Vapor means in this case VOC, so we can know the VOC composition. I already showed this slide to you. So the LNG mole fraction is given by the cargo owner. Okay, I mean that the LNG producer gives us the information. Our LNG has this composition. Then in the process simulator, we input this composition and we set the pressure or temperature. Then we can get the VOC composition. So the VOC composition is calculated by the commercial software, commercial program. Okay? Understand? So as I explained already, methane is the majority for both for LNG and BOG, but nitrogen is trace component for LNG, less than 1%, but it takes around 10% for BOG, because the boiling point, the normal boiling point of nitrogen is less than the methane by 30 Celsius. In other words, nitrogen is more volatile. We use the expression volatile or light. In oil gas industry, heavy light is not related with weight. Ultimately, it is related with molecular weight, but heavy light, the distinction for being heavy or being light is related with the boiling point. The tendency to become a gas. So light means it is likely to go to the gas phase. So the same meaning, light is volatile. So we can say that nitrogen is more volatile than methane. So due to that kind of tendency, nitrogen takes the significant portion in BOG. Another question is, now BOG is generating, so easy way is to remove the BOG, but we can have this. We can stuck in this kind of situation. That the BOG reliquefaction system is not ready to liquefy the BOG. So, in order to avoid overpressure due to the BOG, we can burn the BOG in the gas combustion unit. But the port authority prevent that kind of operation. Please do not operate your gas combustion unit in our port, because there are a lot of ships. So we don't want to see any white gas. That if we generate some heat from the ship, it will. We can see that the steam, actually the condensed water in the air, that is look white. So sometimes port authority don't want to see that kind of things. So the LNG carrier. So the ship owner of the LNG carrier wanted to check what happens if we just close the cargo containment system. So this is the question. So in this case, we have heat ingress from outside, and we cannot remove BOG from the cargo tank. One more better thing is, our cargo tank is a little hot before loading. Usually it is around minus 90 Celsius before the LNG loading because there is no LNG within the cargo tank. So it was a little warmed up due to the external heat ingress. Then we put LNG into this hot tank. Minus 19 is hot compared to minus 160, right? So the hot wall will generate some heat ingress into the cargo tank, into the cargo LNG. That means we can get more BOG than the normal case. Normally, the insulation layer is at minus 160, but when near the loading, just after loading, the cargo tank is a little warm. So we have two kind of heat ingress. One is between temperature difference. The other is the sensible heating by the insulation layer. So the concern is that because we have a warm insulation layer, this layer will generate a lot of BOG. So the cargo tank pressure will rise rapidly. You agree? If you have correct knowledge about phase equilibrium, you can say that that kind of question, that kind of reasoning is not correct. When we increase the temperature of a mixture, it is very hard to increase the temperature because some component will boil up, and the boiling component will take away some large amount of heat due to the phase change. You remember the heating curve for the mixture? So for the multi-component system, it's very hard to increase or decrease the state rapidly. For one component system, if this space, the inner space, is taken by air, then we can expect that the temperature, the pressure will increase due to the temperature increase, according to the ideal gas law. The temperature will increase, volume is constant, so pressure will increase linearly to temperature. Okay, so if we have a heat ingress from outside, the temperature will increase, and in consequence, the pressure will increase. But we have a multi-component system, and the mixture is in boiling state. In that case, what we can expect that the pressure change would not be that large due to the latent heat. And in other words, multi-component system has a kind of buffering capacity. So in this case, I modeled I come up with a multi-block model, and all the cargo tanks is divided n slice, and for one slice we can drive an analytic solution. I'm assuming that the one slice is wetted at once. That for one slice we can calculate we can apply the governing equation. If you saw, for this simple geometry, we can calculate the temperature distribution, and from the temperature distribution, we can calculate the heat flux, right? The heat flux is you remember this equation? Then, if we fill up the cargo tanks with LNG, then if we add the heat flux with the time, then we can get the overall heat ingress. So this is this point T0 is the start of the loading, and this time for loading completed, and if we sum up the heat ingress, we can get heat ingress total. Actually, the heat ingress total is greater than the normal heat ingress by 50%. In other words, in steady state, if we get 100 kilowatt from outside, just after loading, we may have 115 kilowatt. So heat ingress is correct. Heat ingress is correct with our reasoning. The heat ingress will increase because of the hot wall. But if we calculate the phase equilibrium with the heat ingress, the pressure difference is not that much. That this solid line, this dotted line, is the pressure with the design heat ingress. That 100 kilowatt, and this line, the solid line, is P pressure with heat ingress after loading, with the heat ingress minus 150 kilowatt. So you should distinguish the situation when you deal with a gas, one component gas, or when you deal with multi-component gas, and when you deal with multi-component boiling liquid or condensation. So the situation, maybe you are very familiar with this kind of dynamics. This kind of dynamics is applicable, that ideal gas law is applicable to only the one component gas. Okay? If we deal with the multi-component system, the pressure and temperature behavior will deviate from this ideal gas law. If you deal with condensed or boiling multi-component liquid, the situation is totally different from this kind of dynamics. Let's skip further radical fraction system. Instead, I prepared a simple two questions. As gas demand is increased, people started to think about new transportation method. One is pressurized LNG. normally LNG is transported under atmospheric pressure, under 1 bar, right? But people are thinking about what happens if we carry LNG at 10 bar or 20 bar. Actually, this concept was proposed by ExxonMobil. The other one is CNG, compressed natural gas. What if we transport gas compressed to 100 bar to 200? So, in this case, just think about the advantage and the disadvantage from the thermodynamic viewpoint. So, first example, PLNG, pressurized LNG. And in this concept, we are trying to carry LNG at 10 to 30 bar. Then, what are the advantages of this system?
We don't need to drop the temperature of LNG.
Right. It's related with the boiling point. You remember the boiling point curve? Boiling point curve is the boiling pressure is proportional to boiling temperature. Okay? So if we increase the boiling pressure, as I tell again, we are carrying boiling LNG at any case. Okay? So if we increase the boiling pressure, we can increase the boiling temperature. That means if we increase if we carry PLNG, pressurized LNG, maybe the storage temperature is far higher than minus 160, maybe minus 90, maybe minus 80. So if the boiling temperature is increased, what is another benefit? Actually, we have a gas at room temperature. The gas is cooled down. So for normal LNG, initially the gas at 20 Celsius decreased to minus 164 Celsius. If we employ the PLNG concept, the temperature would be minus 80. Then we can save this amount of energy during the liquefaction. What is another? Can you find another advantage? Volume? No. Volume of LNG at 1 bar is nearly the same LNG at 20 bar because liquid is nearly incompressible. Less BOG? Yeah, less BOG. We have less temperature difference. In this case, the temperature difference is 180. In this case, just 100. So the insulation layer would be decreased. The thickness of insulation layer would be decreased. What else? After LNG is, in order for the LNG to be used as a fuel, you should increase the pressure for pipeline transport. Okay? Actually, the LNG is increased, is pressurized to 70 bar, and then it is vaporized for pipeline transport. In Korea, we have 3 LNG terminals. One is Incheon, another is in Pyeongtaek, and the last is in what is the name of the area near the Changwon? Tongyang. Yeah, Tongyang has one LNG terminal. So we have 3 LNG terminal. Actually, KOGAS, Korea Gas Corporation, owns 3 LNG terminal, and POSCO has its own LNG terminal in Yeocheon. So actually, we have 4 LNG terminals. In the terminal, LNG is pumped up, and increased in pressure, and then vaporized. So in the case, we have 20 bar. In this case, it is 1 bar. So we can save the pumping energy. So there are a lot of advantages. What are the disadvantages? Nothing is free. Okay? We increase the pressure, we can find several wonderful advantages, but it has disadvantages. Of course, what is that? One is pressure vessel. We need pressure vessel for 20 bar. And the amount of LNG is very huge. The amount of energy that is carried by one LNG carrier is very huge. That means the cargo tanks should be huge, and that means the pressure vessel should be huge. So it's very difficult to construct that kind of pressure vessel. And the pressure vessel should withstand 20 bar at -80. It's not easy to construct that kind of pressure vessel. What is another disadvantage? Everything fails. Accident happens. So one possible accident scenario for this kind of system is leak. We have a small leak in the tank. If a small hole here, we have a large driving force, 20 bar. And a huge source here, big tank. Then we have a dangerous jet, LNG jet from the tank. So that can damage, if we have this kind of leak, the leak may easily destruct the ship. So another is the safety. Okay? Let's apply the same reasoning to CNG, sorry, not PLNG, CNG, compressed natural gas carrier. So in this concept, we want to compress the gas, and we want to avoid the phase change from gas to LNG. We just compress the gas and try to transport it via carrier. So in this case, we have, let's assume that the storage temperature is 100 bar, is gas, then what are the advantages? All right. Phase change. Making LNG from gaseous natural gas is energy consuming process. That means the latent heat is significantly high, so it's very hard to increase or decrease the temperature or pressure of a boiling system or condensing system. Okay? So in this case, we need just compression. The work for compression, the energy required for compression is chicken feed compared with liquefaction. Consider the equipment for compression. If we have one compressor with some proper cooling system, that's okay. In the well, sometimes the well pressure is around 200 bar. This gas is decreased for processing purpose. I mean that this 200 bar gas is treated in FPSO or a platform, and gas is separated from crude oil, and we can store this gas here directly. Usually the pressure 200 bar is too high. I mean the piping, the equipment to design this high pressure system is difficult. So usually before it reaches the LNG FPSO processing plant, the pressure is usually decreased to 60 bar. So what you can do is to compress 60 bar to 100 bar. That kind of compression is very simple. The compression ratio is less than 2. So if we have a compressor, we can charge the gas into the CNG tank. But for LNG, in order to generate LNG through phase change, we need huge amount of energy and complicated plant system. So energy saving is the first advantage of the CNG carrier. What else? Another thing is also we can discharge this high pressure gas into the pipeline directly. What are the disadvantages? Gas has lower density than liquid. That means if we consider same volume of cargo tank, the mass of LNG is 3 to 4 times greater than the CNG. I mean the mass carried by gas, CNG, is far less than the LNG. And it has another disadvantage, that is volume efficiency. I mean pressure vessels. In order to store this kind of high pressure, we need pressure vessels like pipelines or cylinders. That kind of structure is not volume efficient. I mean, for this kind of LNG, we need just tank like our classroom. But for high pressure gas, we need kind of pressure vessels like the nitrogen gas cylinders in your labs. So the CNG is not very volume efficient. Another thing is also safety. So high pressure, high temperature, low pressure always means safety. Always related with safety. Okay? Some deviation from atmosphere, from atmospheric pressure, atmospheric temperature is a source of hazard. Especially pressure is more important. High temperature is okay, but temperature requires some conduction material to transfer to disperse. But pressurized medium itself has driving force. It can expand. Okay, so high pressure always means high hazard. Okay, that's all I prepared. Oh, conclusion. Thermodynamics is critical to process engineering, and which in turn the core of offshore plant. What is process engineering? Who majored in mechanical engineering? What is mechanical engineering? Yeah, it's too silly question. But what is mechanical engineering in shipbuilding and offshore industry? And what can you, mechanical engineer, do in shipbuilding and offshore industry? You can design structure, you can design machinery, you can design heat transfer equipment like heat exchanger. Then, what is process engineering? Process engineering, the main concern of process engineering is first sizing. That they want to decide the capacity of the compressor, the heating or cooling capacity of the heat exchanger. So, in other words, if you are a mechanical engineer, you need information about the boundary condition, including the capacity. So the job of process engineering, the job of process engineers are to make a decision on the capacity. Or the role of process engineers is to specify the functions of the equipment or the plant itself. So that kind of process engineering is critical to offshore plant. And if you wanted to be process engineer, you should master thermodynamics. But it requires several years of experience, so you don't have to be hurry. Okay, the industry, the people around you, the software will help you learn the thermodynamics. We have many commercial process simulators. I think some of you already use some process simulator or the CFD codes or the structural programs. Nowadays, there are a lot of programs. Usually, the programs are more expert. They are better than 99% of the engineers. They can do everything except one thing. One thing is creation. Okay? Creating a system is impossible by any commercial code. They don't know about the system. They don't know about the system structure. They don't know about initial condition or boundary condition. What can they do is calculation. Okay, solving partial or ordinary differential equation. So what I recommend to you is that you should be creative. Okay, your calculation capacity is the importance of your calculation ability has less and less meaning as time goes on. So you should understand the fundamentals, and you should create some new system. Okay, but my statement can apply to all of you, even though you are a process engineer or mechanical engineer, structural engineer, instrument engineer. Anyone has their, if you are a researcher, you will be requested to come up with a new idea, new system. Okay. And in terms of thermodynamics, the process simulator will help you. So don't worry about the details. Okay. In the future, I'm sure you will be faced with thermodynamic confusing problems. Okay, thermodynamics is always confusing. It's not mathematics. It's not like mathematics. It's about the behavior of material, the gas, liquid, air we are dealing with. When you face this kind of confusing problems, count on the first principles. The first principles are conservation of mass, moment, and energy. So if you check your thermodynamic handbook or the book Transport Phenomena written by Bird, Stewart, and Lightfoot will help you greatly. I promise. Okay, thank you.